Welcome everyone. For today's prep, we're going to start to look at the second derivative test. So we've looked a little bit at the first derivative test. Now we're going to look at the second derivative test. And this is just another method we can use to classify our critical numbers. So once we find the critical numbers, we're going to have another option for how to actually classify them. So we'll see that we can either classify them as a min or a max using this test. So let's look at the test, what the test actually says. And again, we're using this to just classify our critical numbers as either a maximum or a minimum. So let's say that we found a critical number x equals c. And this is one of our special, most common critical numbers where the derivative is equal to 0. So we know critical numbers happen two ways, usually. So when we find a critical number, that's usually the first step. So how do we actually find our critical number? Well, we calculate the first derivative, try to factor it, and then we look for places where either the first derivative is equal to 0 or where our first derivative does not exist. These are the two ways we can have a critical number. And once we locate the x values here, once we locate these x values, then we want to classify them. So do we have a max or a min? Now, we've seen these are the most common way we get critical numbers, where our derivative is equal to 0. So the second derivative test only works for these ones. It doesn't work for these. So for these, you'd have to use the first derivative test. So our second derivative test doesn't work for these ones. All right, but that's not too bad because we saw most of the functions we've been looking at don't really have these types of critical numbers. There's been a few we've seen, but these are definitely less common than in the types of functions we look at. All right, so once we find our critical numbers, we want to go to classify them. And what this test says is that we're going to plug our critical number into the second derivative, and we're just going to see, is the result positive or is it negative? And if it's negative, then our function has a local max at that critical number. And if it's positive, then our function has a local min. Now, there's another issue with the second derivative tests. Sometimes we have critical numbers where it doesn't work. And sometimes, even if it is a perfectly good critical number, the second derivative test can be inconclusive. So this is kind of another little issue with it. Sometimes it happens. For the most part, though, this test works out nicely, but it can be inconclusive. So if it's inconclusive, then, again, you have to use the first derivative test. So inconclusive means you don't know. We don't know what's going on there. Could be a max, could be a min, could be neither. So inconclusive means we just don't know. So you have to try the first derivative test instead. All right, so what's a way to remember this? So if we think about what does the second derivative tell us? When we're talking about being either negative or positive, the second derivative is telling us about concavity. So when we do this test, we're going to kind of relate it back to concavity. So let's suppose that we plug in our critical number into our second derivative, and we find that this is positive. So we find our critical number, plug it into our second derivative, and we get a positive result. How can we remember that our function is going to have a local min? Well, let's think about what positive second derivative means. Positive second derivative means concave up. So, draw the concave up shape. And after you draw the shape, well, what does it look like? Are you going to have a high point or a low point? And we're going to have a low point on our graph. So, local min. at x equals c. And this test is a little counterintuitive. Normally when we think of positive, we think it's a good thing, so we're thinking it's a max. It's kind of the opposite here. When the second derivative is positive, we actually end up with a low spot. And if we do our second derivative, plug in our critical number, and we get a negative, well, normally negative, you're thinking, oh, it's going to be a bad thing. Well, what does negative second derivative mean in terms of concavity? It means concave down. Again, draw the shape. What does concave down mean? Shape-wise, it means it's going to look something like this. And, well, it looks like we're going to have a high point, and that's precisely what this test says. We're going to have a local max at our critical number. So when our second derivative is negative, we have a local max. So again, it's a little counterintuitive. When you think something's negative, you think, oh, it's going to be small. It's going to be low. And it's kind of the opposite here. So really, to help remember this test, draw the shape of concave up, concave down. All right. So let's try one example. And we're just going to see how this test works. So let's suppose that we have a function f, and we've already gone through all the work. We found the critical numbers of this function. So let's suppose that we've found x equals 1 as a critical number and x equals -2 as a critical number. So we want to classify these critical numbers as either, what's going on at x equals 1? Is it a min or a max? Same thing at x equals -2. We know something special could happen there, but we want to know, is it going to be a min or a max? And we're going to use the second derivative, f double prime, which we've just so happened that it's already calculated for us, to actually classify these critical numbers. So we're going to use our second derivative test. And a lot of times I'll abbreviate this, second D test. And how do we do it? Well, we take each of our critical numbers, so x equals 1 and x equals -2, and all we're going to do is just plug these in to our formula for our second derivative. So we'll plug 1 into our second derivative, and let's see what we get. So wherever we see an x here, we're just going to change it to a 1. And powers of 1 are just 1. So we end up with 4 minus 15 plus 2 plus 21. And if we simplify that, we end up with 12. Now, the number itself, we're not too worried about that number. We just want to know, is this number positive or negative? And in this case, it's positive. So once you identify the number as either positive or negative, draw the shape. So positive means concave up. So draw the concave up shape. I want to see this as part of your work, just so it helps you remember the test. So we have our concave up shape, and now we can clearly say that we're going to have a local min at x equals 1. And that's it. It's a nice, quick test. So the second derivative test is probably the one we'll use a bit more because it is a bit quicker than the first derivative test. The only downside is it does have this sort of issue where sometimes it can be inconclusive and sometimes we can't do all of our critical numbers. But for the most part, this is not really an issue for the functions we're going to be looking at. And this doesn't happen too often where we get this inconclusive result. So in general, second derivative test, nice and quick. So let's try the other critical number here. So we want to see what's going on at x equals -2, this other critical number. So we're going to plug it into our second derivative. And when we do that, let's kind of go through and evaluate. So we're going to end up with 4 times -2 cubed minus 15 times negative 2 squared plus 2 times negative 2 plus 21. All right, so we got to simplify this down, and we don't have to, we're not really worried about the number. We just want to know, is it positive or negative? So this first part here, negative 2 cubed, that's going to be negative 8. And then negative 8 times 4 is going to be negative 32. Okay. Then negative 2 squared, that's going to be positive 4. And then we're multiplying positive 4 by negative 15. So that's going to be negative 60. All right, so far things aren't looking too good. We got negative 32 minus 60. Then we've got 2 times negative 2. Well, it's negative 4. And then we've got plus 21. So this is negative 96. And then we're adding in positive 21. So this is going to be negative 75. Hope I did that right. Negative 32 minus 60, negative 92, negative 96. And then, yeah, I think that's good. In any case, we don't really care about that number. We just care about the sign. And negative 30, all this stuff is definitely going to be bigger than positive 21 in terms of size. So the story is, this is negative. Negative means concave down. Draw the concave down shape. And what does it look like? Well, looks like imagine if we were standing on our curve, we're up here, it's downhill in both directions. Well, it's going to be a local max. So what we're seeing is we have a local max at this critical number. All right. So we've got one critical number where we had a local min, one where we have a local max. So this test, like I said, really quick. So this, in some of the later sections where we're doing more applied problems, this will probably be our go-to derivative test. But the first derivative test is perfectly good. And if you're finding the intervals of increase, decrease, well then you've already, basically you can just read your sign chart and answer the question. So we're going to practice more of these in class along with our first derivative test. So we'll see you then. Bye-bye.